Welcome to structural dynamics class. So in this class we will study about dynamics of non-structural elements. So these non-structural elements are of two types. One is force based non-structural elements and second one is deformation based non-structural elements. Say a simple example like this: if you take a bottle, okay, so this is almost a rigid body kind of thing, and it behaves like if I do the shaking, so it may topple or it may slide or it may rock. So these are rigid blocks. So this is one type of non-structural element. Other type of non-structural element is say along say pipelines which are there inside the building. So these two are non-structural elements. So in this class we are going to study non-structural elements which are rigid in nature. So for example, say a furniture in the building, say a water tanks on the rooftop of building, and say our electronic equipments which are placed on tables also, all these come under rigid non-structural elements. So they don't have internal deformation, but they may slide, they may rock, they may topple. So during earthquakes, even if the structure is, the building is safe, there are a lot of injuries leading to death sometimes, mainly due to non-structural elements. Non-structural elements we will discuss. So what are non-structural elements? So you can see this one, say glass facade. Okay, so that is a non-structural element, as you can see in this slide. And then you can see heavy facades. So these days, especially in urban areas, so glass panels as big as 3 meter by 3 meter glass panels are installed at the top, say maybe 30 meters height, 40 meters height. So we need to understand the dynamics of these non-structural elements. This is, you can see in this one, this is bare frame, and then the finished one will have so many non-structural elements. So like say ducts, ceilings, sprinklers, partitions, furniture, lighting arrangement, air conditioning units, so many things are there. As you can see this one, so during earthquakes, because of deformation and also because of forces, so they got damaged. This is imposed deformation, and you can see deformation of the rack, and also you can see like equipment. So this is a secondary disaster. This is also non-structural element. So but mainly we will study non-structural elements which are rigid in nature. So how dynamics of that will play. Indirect losses due to this and this furniture behavior. So let me show you a small video clip which is describing this furniture behavior. Long boundary walls also act as a non-structural element or rigid block dynamics, and you can see this is another view, another example. So there are three sets of these non-structural elements. One is building facades. So for example, glass walling on the perimeter, and then building contents, that is example furniture and say equipments, and then building services, so electrical wires, water pipelines. So we are mainly focusing on this contents of the building in this class. So they are of the type, those that are affected by force. So they are stiff and massive. So for example, it's a diesel generator installed inside the building. And those that are affected by displacement, so they are flexible and tight. So for example, water pipelines. And those that are affected by both flexible as well as massive hoardings, billboards, like that. Like solution to this one is like you tie it down. So tie down. Here you can see we are tying it down. Horizontally, vertically we are tying it down. The second solution is bolt down. And the third solution is falling debris. So you put some safety over the equipment. So this is protective canopy. So these three solutions are there, but for executing these solutions we need to do some calculations. So what should be the strength of these protections? Okay, so you can see this one. Okay, tightening of bolts very hard, so shaking of floor transformed to equipment from base to on the roof. So we'll solve an example problem and understand this one. So tightening of bolts very hard. So shaking of the floor transferred to the equipment. So equipment can get damaged. So that is another issue we need to address. And not anchoring at all. So then it may cause sliding failure of the equipment. So these non-structural elements of building are ones which are not part of any load resisting system of the building, and hence these are often neglected from the design point of view. So but past earthquakes clearly point out the poor performance of several buildings due to the inadequacy of design provisions for the non-structural elements. So motion of non-structural elements inside the building. So objects inside a building can slide, can rock or topple when a building is subjected to random shaking. So the first example is, say this is a non-structural element, so whose weight is given by W, and earthquake force is acting at say center of mass, and say center of mass is exactly at h by 2, and from in the horizontal direction b by 2, breadth by 2 and height by 2. So if sliding means what? So when the motion is given, then it slides in horizontal direction. Then it can also rock depending on certain conditions which we will discuss. And then third one is topple. So it can slide, it can rock, or it can topple. So all these three things we need to avoid. Sliding and rocking, this is a combined thing. So the base of the non-structural element is completely in contact with the surface on which it is rested. This is because of the friction, but is horizontally translating on the surface with friction. So it is horizontally translating. And then rocking. So non-structural element is not sliding, but it is locked at the toe and lifts its head, something like this. Okay, so if you move it, then it is locked at the toe and it is lifting from the heel, or if you look at from other direction, it is locked at the toe here and lifting from the heel. Then third one is toppling. So toppling is non-structural element is rocking, losing its balance, finally ends up sideways on the surface. So when this condition comes, we will discuss. So these conditions depend on geometry of the object, ground shaking, and then frictional resistance. So governing conditions for only sliding. So when push is more than frictional resistance, and second condition, restoring moment is more than overturning moment. So let me discuss this one. So as we know, weight, say on the base, if weight is acting and we want to push, so this push, that is force of earthquake, has to overcome weight times frictional resistance. So that means what? Force is equal to, earthquake force is equal to mass of the object into earthquake acceleration, should be greater than frictional resistance. Weight means again mass into gravity, mass of the object. So this mass of the object can be removed. So if acceleration is greater than frictional resistance times gravity, it will slide. So that's how this equation is governing the sliding, only sliding condition. So that means what? A should be greater than mu g. It is interesting to note here that geometry is not in the picture. So then the second one is overturning moment and restoring moment. So overturning moment, if I look at it, so from this is F earthquake h by 2. So moment, say if I take at this point, so this force F multiplied by lever arm, that is F into h by 2, is equal to W. So this is in the clockwise direction, force into h by 2 is clockwise direction, W is weight, weight into b by 2 is in anti-clockwise direction. So this, if it has to overturn, moment due to applied force should be greater than this one, but for not overturning, only sliding condition, this has to be less. So F into h by 2 should be less than W into b by 2. So F, we know, m into AQ, earthquake acceleration multiplied by mass, multiplied by h by 2 should be less than m into g into b by 2. So if you strike off m, then what we get is acceleration should be less than g multiplied by aspect ratio. So b by h is aspect ratio. So acceleration less than g into b by h is the condition. So two conditions are there for only sliding case. So acceleration should be greater than frictional resistance times gravity, and again acceleration should be less than gravity times aspect ratio. So then sliding only case will take place. That means object will only slide. The second case, only rocking. In only rocking, frictional resistance is more than push. So that means what, we cannot push. But at the same time, overturning moment is more than restoring moment. So this is a similar case but slight change in the condition. Here this earthquake acceleration is peak acceleration. So earthquake acceleration should be less than friction times gravity. Here earthquake acceleration should be gravity times aspect ratio, it should be greater than that. So these are two conditions for only rocking. Earlier case was only sliding, second case is only rocking. And the third one is toppling. In toppling, overturning moment is more than restoring moment. Also frictional resistance is more than push. So in that case, A, acceleration, peak acceleration is less than gravity times aspect ratio, B by H. The second equation can be derived from simplifying the nonlinear governing differential equation for toppling. So what is that? Let us look at it. So this is nonlinear governing solution of nonlinear governing differential equation for toppling condition. So if acceleration is more than alpha times g multiplied by 1 plus 1 by 6 into omega by p. So now what is this p and omega we will discuss now. So omega is a forcing frequency. So as long as Cg, center of gravity, remains within the width, inertia force causes overturning moment about point A. So this is a point around which overturning is taking place. Gravity force causes restoring moment. So this we all know. Once Cg crosses B, both cause overturning moment resulting in toppling of non-structural element. So it is something like this. Okay. So this is a overturning moment and this is a restoring moment. So if we take from this point moments, so if the Cg crosses this vertical line, then both will act in the same direction. So currently what is happening is applied force is acting in clockwise direction and then restoring moment is acting in the anti-clockwise direction. So that is why there is a balance. But if restoring moment, that Cg of this one crosses vertical line, then applied force and restoring moment both act in the same direction. So thereby non-structural element will topple. So it's something like this. You can see this one. This is case 1. This is case 2. In case 1, moment due to applied force is acting in clockwise direction. Restoring moment is in anti-clockwise direction. Here, once the Cg has crossed the line, vertical line, then applied force creating moment in clockwise direction, and also self weight is creating moment in clockwise direction. So this is a condition for toppling. Now let us look at the equation for toppling. So we can derive that governing differential equation from the picture, the drawing free body diagram. So I is a moment of inertia, okay, with theta double dot. This is rotational moment of inertia with theta double dot plus mgr sine alpha minus theta. So alpha is the angle with which non-structural element is getting lifted. This is alpha, and theta is, this is theta. So as you can see, sine alpha minus theta is equal to, so restoring, that is m earthquake acceleration multiplied by r cos alpha minus theta. So this alpha minus theta, so when alpha is increasing, okay, alpha is a, you can consider this as a degree of freedom. When alpha is increasing, if it is equal to theta, then toppling condition takes place. So theta is greater than 0, and we have another one, theta less than 0. So this is from this location, theta is greater than 0, and from this location on the other side, it is theta less than 0. This we use this equation. So two equations we use. So assuming earthquake excitation to be sinusoidal and equations are linearized into, so what we get is a solution. Theta is a degree of freedom, so we need solution for theta. So this is a non-linear equation. So we need to solve this by doing linearization. So that P is frequency ratio, that is 3G by 4R. P is a frequency parameter. So where R is from center of mass or center of gravity up to the diagonal length is R. On solving we get this theta a very complex equation. Then conditions for toppling z is equal to alpha minus theta, z double dot is minus theta, then finally equation becomes this. For small angles we use this equation, complex equation, and solving we get z, this is in frequency domain. So with this we get the condition acceleration, peak acceleration if it is greater than g times all this factor, so that is a condition for toppling. So that this is a simplified form, so what I have shown you in the previous slides. So if you draw the graph between say a frequency parameter and forcing frequency and normalized acceleration value, so this is a condition for safe and unsafe region. So if like if acceleration ratio is crossing this line, it is unsafe for the rigid block, and if it is below this one, it is safe. So this is a necessary condition for designing the safety of rigid blocks. Now for governing equations, for governing conditions for sliding, rocking and toppling. So for us to design, if acceleration is greater than friction times gravity, and acceleration is greater than less than gravity times aspect ratio, when these two conditions are met, then sliding takes place. When acceleration is less than mu times gravity and acceleration is greater than g times aspect ratio, rocking takes place. And toppling is this condition, acceleration is less than g times aspect ratio, as well as acceleration is greater than alpha g 1 plus 1 by 6 into omega by p. So these are the governing conditions. In summary, what we have discussed in this class of dynamics of non-structural elements. So there are many non-structural elements which are in the building. So earlier non-structural elements cost percentage was around 10-15%, but these days non-structural elements cost is as high as 80% of the total building cost. But the issue is these non-structural elements are not taken into consideration while doing the design. So that's why even if the main structure is safe, sometimes there are severe injuries leading to death just because of the non-structural elements behavior, dynamic behavior. So what we have studied was in this class non-structural elements which are rigid in nature, how they behave. So either they slide, they rock, or they topple. So what are the necessary conditions for sliding, rocking and toppling? So we have discussed in this class. So in the next class we will solve one numerical problem of designing the safety of non-structural elements.